Okay. Okay, you can start, Amanda.
So welcome everyone to this week's One World Property Seminars. So before I introduce today's speaker, just a couple of announcements. So the first one is that next week we have Sylvie Mayer and Jiviet Tran speaking. And then the second thing is for those of you who are new to these seminars, if you have questions during the seminar, the easiest way to ask them is just to type them into the chat, and either other experts in the audience can answer them, or if not, then Alessandra or I will relay them to the speaker. So in that case, I'd now like to welcome our first speaker today, who is Matthias Erbar from Bielefeld, and he'll be speaking on optimal transport and gradient flows in discrete or non-local settings.
Okay, thank you very much for the introduction, Amanda. Thank you very much for the opportunity to speak here. It's really a pleasure to speak in this today's session of the seminar together with Jan later on. In my talk, I would like to give you an overview of a couple of results that make tools and ideas from optimal transport available for stochastic dynamics beyond diffusions, namely for stochastic systems with, say, discrete or otherwise non-local interactions. I have to apologize right away. I was intending to do this talk in a hybrid format, writing on my slides as I go, but just when I came to the office, I dropped my pen once too often and it died. So what you see is kind of the last minute attempt to make this into a slide-only presentation. I apologize for any inconvenience this might cause. Okay, so let me start by giving you the general idea and an overview of the talk. So the paradigm behind what I will be presenting is the idea that the behavior of stochastic processes should be tightly linked to the geometry of the underlying space. This goes in a two-way direction. On the one hand, having a precise understanding of the geometry of the base space should one give good control of the stochastic process in question. And on the other hand, stochastic processes might also be used or are very useful tools to explore the geometry of spaces. So this is there's a long success story behind this, for instance, in the Barclay-Emery theory to Markov diffusions, or the Lott-Villani-Sturm theory for spaces with synthetic curvature bounds. Now, optimal transport comes into play by giving a geometric point of view on the evolution of the stochastic process in the space of probability measures, and gives tools such as gradient flow descriptions to get hands-on the process. This is very well understood for diffusive processes, yet many systems of interest are beyond the scope of this classic picture. They might live on discrete spaces or otherwise singular spaces. And what the goal of the talk will be to show you some developments, how ideas from optimal transport can be transferred to that setting. So the plan for the talk will be to first give you an overview of, say, the classical picture of optimal transport and gradient flows to set the stage. And then mainly focus on discrete stochastic dynamics and stochastic dynamics for particle systems with non-local effects, and in particular related to the Boltzmann equation, to show you how they can be viewed as gradient flows by using suitably adapted transport geometries. Okay, so let me start by recalling some basics of optimal transport. The basic building block is the so-called Kantorowicz-Wasserstein distance. It's defined by an optimal transport problem given two measures mu0 and mu1. We ask for the most efficient way of transporting the first measure onto the second measure, where efficiency is measured by requiring that the cost of one unit of mass to be moved from x to y. This may be given by the squared distance between x and y. There are other choices of cost functions possible. And then we ask for a plan to do this in an efficient manner. And a probabilistic take on this is to look for the joint law of two random variables x and y that are distributed according to mu0 and to mu1 respectively, and minimize over this joint law the expected squared distance between x and y. We can also reformulate this in terms of couplings. So a transport plan might be a measure on the product space, which tells us how much mass is transported from near x to near y. And then we look at the total transport cost, integrating the cost function against this transport plan and minimizing over all such plans. There's a very nice dynamic perspective on this that was discovered by Benamou and Brunier in 2000, which recasts this Wasserstein distance as a dynamic optimization problem. So here, the idea is to connect the given measures mu0 and mu1 by a curve of measures mu_t. This curve is described by a continuity equation. Partial t of mu_t is divergence of mu times a vector field gradient psi. So the intuitive picture is that as we move along this interpolation, the individual particles travel by the velocity gradient of psi. And then what we're minimizing is kind of the total kinetic energy that is needed to transform the first measure into the second one. This is the velocity squared times the mass, and then integrated in space and time. With a slight change of variables, replacing this mu times gradient psi just with a vector field j, this can be turned into a nice convex optimization problem. The continuity equation then becomes a linear equation, and mu and the new variable j, and the quantity to be minimized is the momentum squared divided by the mass. And this is convex in j and mu. Okay, this Kantorowicz distance equips the space of probability measures with a distance that inherits many nice properties from the underlying space. And in particular, minimizers in this dynamic problem, they are geodesics with respect to this distance, or shortest curves when measured with this distance. One very useful connection of optimal transport with stochastic dynamics is the idea of gradient flows in the Wasserstein space. And it's by now well known that many evolution equations can be cast as steepest descents or gradient flows of a certain free energy in the Wasserstein geometry, starting from the seminal work of Jordan, Kinderlehrer, and Otto in the late 90s. Typical example are, for instance, Makin-Vlasov equations, where partial t of rho is given by a diffusion component, Laplacian of rho, plus the divergence of rho times the gradient of an external potential V and the gradient of an interaction potential W convolved with rho. This is the gradient flow with respect to the Wasserstein distance of a certain free energy functional, which is the usual Boltzmann entropy plus an internal energy given by the potential V and an interaction potential built from the interaction energy W. So behind this interpretation is the so-called autocalculus, so the idea to equip the space of probability measures with a viewing this as formally as a Riemannian manifold, and the evolution equation as a steepest descent in this manifold. Since this will be a recurring theme in the talk, let me try to give you a 1-minute explanation of this gradient flow interpretation. So here's a schematic picture where our surrounding space is the space of probability measures, and the free energy gives us kind of a landscape in which the evolution equation evolves by following the direction of steepest descent. Okay, so how does this Riemannian interpretation work? So for, say, a classical gradient flow, it's usually given by the equation by a curve x dot is minus the gradient of some function e at x. A more convenient way to write this to disentangle the role of the functional and the geometry is to write this as minus some operator k times the differential of this function. where this operator is some function that identifies the cotangent with the tangent space. If we view this as a curve in a smooth manifold. Now here in our case, our manifold is formally the space of probability measures. This operator can be chosen to be minus the divergence of rho times gradient of the function phi. And in the example that I put above here, what is free energy, its differential would be the logarithm of rho, the potential V, and the potential W convolved with rho. So
we have a question in the chat just asking, is it a linear equation?
No, it's not a linear equation. Sorry, there's probably a bracket too much. I'm very sorry, that's a typo. So here this bracket that I'm pointing at is superfluous. So the last term is quadratic in rho, with the rho here in front and the convolution in rho here in the back. So sorry for this typo. Does this clarify the question?
I think so. Yes, thank you.
Okay, sorry. Okay, so if we put everything together, then we see that indeed this equation takes formally the form of a gradient flow. One can also, so if we think of this identification here determining our geometry, so this in the classical setting, this would just be the inverse of the metric tensor. The kind of the length of a tangent vector we can measure by identifying this with a cotangent object via the operator k, and then taking the pairing of psi with this operator applied to psi. If we do this with this choice, we get precisely this integral of gradient psi squared times rho. And this is precisely the thing we were minimizing over in the dynamic formulation of the Wasserstein distance. So indeed, the Wasserstein distance is kind of the induced global distance that comes from this local Riemannian structure. Okay, so this to make this picture rigorous, one possibility is to give a variational characterization in terms of the equation via an energy dissipation identity. So note that in the abstract setup, if we have an arbitrary curve x and we look at the rate of change of the function e along this curve, we can always bound this. So this will be gradient of e paired with x dot. We can always bound this from below by Cauchy-Schwarz with -1/2 the speed of x squared and the gradient of e squared. And the crucial point is that we will have identity here in this estimate if and only if the curve is the gradient flow. So if we port this to the Wasserstein space, if we integrate this in time, we will kind of get the e at the final time minus e at the initial time, and then an integral over these quantities. So in our setup, we look at the functional, the internal energy at final time minus internal energy at initial time, plus an integral of the speed of the curve, which here this role is taken by the speed with respect to the Wasserstein distance, and the role of the squared of the gradient is taken by the dissipation. That is the rate of change of the free energy along the dissipation. No? And then the characterization is that this functional is always non-negative, and the gradient flow is precisely the curve which sets this function to 0. So there's nice information about the dynamics can be gained if some properties of the functional are available, namely if the functional is what is called displacement convex. This gives a strong control on the dynamics. So displacement convexity means that the functional is, say, strictly convex with a positive constant along each shortest curve in the Wasserstein space. And when we have this property, this gives rise, for instance, to log Sobolev type inequality, where we get an estimate of the free energy, maybe minus its minimal value, in terms of the dissipation of the free energy. And this in turn gives nice control on the trend to equilibrium for the evolution. Namely, we have exponential convergence of this reduced free energy, and we have also exponential contraction when measured in, for instance, in Wasserstein distance. The intuition behind this is if we're following the gradient flow in this landscape here, if we are in a situation where this landscape is strictly convex, then the steepest descent will contract exponentially. Okay, so for these kind of diffusive equations, there's a quite complete picture, and these are powerful tools. Yet unfortunately, many systems of interest they lie outside of the scope, and I will try to highlight a couple of situations where where these ideas can be transformed to discuss more general classes of equations. So I will major focus will be on stochastic dynamics in a discrete setup. So what is the setting we're considering? We look at a finite state space X and consider an irreducible continuous time Markov chain on the set that is given in terms of certain transition rates. Let's call them Qxy. So this would be the rate at which the process jumps from side X to side Y. We assume that the dynamics is reversible, so the unique invariant measure satisfies the detailed balance condition. And in this setup, of course, the Kolmogorov forward equation describes us the evolution of the law of the Markov chain. If we denote this law by mt, then it tells us that the time derivative of mt is given by a sum. So at x is given by a sum over all y of qyx m and y. So this is the total flux into x minus the total flux out of x, which is the sum over y qxy times m of x. Okay. Now, of course, we can ask the question, okay, why don't we use plane optimal transport to describe this situation? The problem is that the classical Wasserstein geometry degenerates on discrete state spaces. So any non-trivial curve in Wasserstein distance would need to be constant. So in particular, there are no shortest curves, no geodesics, and no chance to see any gradient flows. Yet the situation can be changed by, saved by looking at geometry on the space of probability measures that's more adapted to the discrete dynamics. This was a result by Jan Maas and Alex Mielke 2011 in parallel, which states that the Kolmogorov forward equation has a gradient flow structure in the space of probability measures by being a steepest descent of the usual relative entropy. It's denoted by end of m and pi, and it's just the sum of m of x logarithm of m of x over pi of x. So it's just the Kullback-Leibler divergence between m and pi with respect to a suitable discrete dynamical transport metric. Okay, and also Jan's talk later on will be very much concerned with this discrete dynamical transport metric. So let me take a little bit of time to introduce this object to you. So first of all, let us try to guess what the right geometry might be by looking at a gradient flow structure from a formal level. And let us try to identify the geometry by identifying this operator k, which describes the geometry. So we can rewrite the Kolmogorov forward equation as a gradient flow of the relative entropy if we choose this operator k here, which is also called an Onsager operator, in the following way. The operator acting on a function psi, we take it to be, we first take a discrete gradient of psi, so just a finite difference. We multiply this by a suitable weight function, lambda, which takes a certain mean between m of x times the jump rate from x to y, and m of y times the jump rate of y to x. And then take a discrete divergence, so sum over all neighbors y of x. So this might look very familiar to the operator we saw on the continuous setup for the Wasserstein distance. There we also had a gradient, a divergence, and a multiplication with rho. So let me briefly jump back to there. Yeah. So what I was just showing is the discrete analog of this quantity here. And since we're in a discrete and non-local setup, this simple multiplication with rho here takes a more complicated form. And a sensible thing to consider for this weight function turned out to be the logarithmic mean. So the mean between r and s is r minus s divided by log r minus log s. The differential of the entropy in this setup is just the logarithm of the quotient of the measure at x and the measure pi at x. So if we put this together, we will see here, if we apply this operator to the differential of the entropy, we will see here a difference of logarithms. Weighting this with this logarithmic mean, the difference of the logarithms will cancel. We're left with a difference of this quotient itself, and this will produce the Kolmogorov forward equation. Okay, so let's try to see how this structure gives rise to a transport distance in a discrete setup. And again, the idea will be to get inspired by the dynamic formulation for the usual Kantorowicz distance. So there we were minimizing over interpolating curves subject to a certain continuity equation. So this will also happen here. So in the discrete setup, we say that a pair M and J is a solution to the continuity equation. So if M is a curve in the space of probability measures over X, and J is a discrete vector field, by which I mean a time-dependent quantity depending on two indices X and Y, and which is antisymmetric in X and Y. And the continuity equation then reads the rate of change of the measure at point X is given by a discrete divergence of this vector field. So we sum over all Y, this vector field at X and Y. Okay, and then the discrete optimal transport distance can be defined by minimizing over, so given two measures M0 and M1, minimizing over all connecting curves between these two measures, subject to the continuity equation. And what we minimize is a certain discrete kinetic energy. So we take the square of this vector field and divide by the mean of M times Q at X and Y, and with the roles of X and Y reversed. So this again is very much inspired by the continuous picture where Benamou and Brunier found this to be a dynamic formulation of the classical Wasserstein distance. And indeed, this distance is precisely the distance that is induced by this local geometry. Okay, a couple of remarks on this object. So in contrast to the usual Wasserstein distance, which was degenerate, this new distance turns out to be indeed a geodesic distance. So there exist minimizers, and we can connect any two measures in an optimal way. It also admits for a nice dual formulation in terms of discrete version of subsolutions to the Hamilton-Jacobi equation. So what for the classical Wasserstein distance would be the Kantorowicz duality. Here it takes the following form. This dynamic minimization problem is dual to a dynamic maximization problem, where we maximize over all functions phi in a suitable class the integral of phi at time 1 against m1 minus phi at time 0 integrated against m0. And what this class is the class of functions that satisfy a discrete type of Hamilton-Jacobi equation. So we ask whenever we test this function against a measure mu, its time derivative plus 1/2 the gradient squared should be less than 0. And there's a slight twist here, which makes things more complicated than in the continuous setup. This Hamilton-Jacobi equation is not decoupled from the evolution of the measure m, but they're intertwined in a certain way through the Zornsager operator appearing here in between the gradients. But nevertheless, this gives a useful dual formulation. Unfortunately, due to this intertwining, there is no equivalent static formulation. So we need to keep this time-dependent picture in the discrete setup. There's no equivalent formulation in terms of couplings, for instance. So this discrete transport problem turns out to be often consistent with the classical Wasserstein distance if we pass to the limit in a discrete to continuous scaling limit. So Jan will tell us much more about this, and I write often here because there are also interesting effects depending on how discretizations are chosen and one has to pay attention here to end up with the correct Wasserstein distance. This discrete approach allows to carry over the very useful tools of displacement convexity to a discrete setup. So one can study the convexity of the relative entropy along geodesics in this new transport distance. And indeed, strict convexity entails a number of functional inequalities like modified logarithmic Sobolev inequalities, discrete Poincare inequalities, entropy transport-like inequalities, as we showed together with Jan a couple of years ago.
Sorry, there's been another question in the chat. It says the W is Wasserstein or not?
This curly W is the discrete object that was defined on the previous slide. It's this object. Sorry, this is probably not so discernible. So the Wasserstein was a straight font W.
Thank you.
And these functional inequalities, of course, give strong control under the stochastic dynamics and control the trend to equilibrium. And indeed, this convexity can be checked in many models, like spin systems, hardcore models, zero range dynamics. Okay, let me move on by looking at more complicated stochastic dynamics with interactions. In particular, I would like to present to you an extension of these ideas to discrete stochastic dynamics with mean field interactions. So we keep our discrete state space X, and we look at an interacting particle system of n particles on this state space. And we will be concerned with the case where these interactions can be thought of mean field type. So one way to describe this is in terms of a Markov chain dynamics on the product space. So there will be an equilibrium measure for the dynamics, which is a certain Gibbs type measure. Let's denote this by pi n. It's proportional to the e to the minus some Hamiltonian u. And the mean field character of the interactions is reflected in the fact that this Hamiltonian only depends on the position of the particles through their empirical measure, which we denote by mn. It's the sum of the deltas in the positions of the particles. This is a probability measure on the underlying space X. So typical choice for this Hamiltonian that would be a discrete analog of the McKean-Vlasov equation that we started out with in the continuum would be the following. Would just be an energy which comes from an external potential V. So we sum up the external potential in the sides of the particles, and there's an interaction potential W, and we sum up the interactions between all the particles xi and xj. Now there's many choices of dynamics which have this equilibrium as an invariant measure. For instance, suitable Glaube dynamics, but the feature that we want to keep is that also the dynamics only looks at the mean field interaction. So also depends on the empirical measure of the particle. So jump in particular, if particle I is to jump from X to Y, this is given by a rate Q from position Xi to new position Y. But this rate might depend, of course, on the position of all the other particles, but only through the empirical measure. One can look at the mean field limit of this particle system. So asking what will happen, how will the law of a typical particle evolve if we let the number of particles tend to infinity? And what one finds is that this should be an mn, not a mu n here. This empirical measure converges to a limiting measure mt almost surely, where this mt solves a certain evolution equation, which looks very much like the Kolmogorov-Forward equation for a Markov chain, but now has some nonlinear effect. So the rate in this equation depends on the current measure. So in this sense, you might call this a non-local, a non-linear Markov chain, if you like. Okay, so these rates will, in our setup, be reversible with respect to what you might call a local Gibbs measure, which also depends on the current state M. And this is given as proportional to e to the minus some Hamiltonian h at x, where this Hamiltonian h is given by taking the original function u from the Hamiltonian of the particle system and taking a derivative with respect to the mass of the at position x. Okay, again, in the McKean-Vlasov, discrete McKean-Vlasov case, this is the usual kind of local equilibrium that you might expect. And now global equilibria of the dynamics, let's denote them by pi star. They precisely correspond to fixed points of this local equilibrium map pi. So pi star is an equilibrium if and only if pi star is its own local equilibrium. Of course, equilibria in this setup, they are in general not unique, and these models can undergo phase transitions if you modify certain parameters. Okay, there is for this nonlinear Markov chains, there's a very similar gradient flow structure hidden behind them that we discovered together with Max Vati, Voyas Lashos, and André Schlichting a couple of years ago. The driving functional behind this gradient flow structure is a certain free energy, which is the usual Boltzmann usual Boltzmann entropy plus our Hamiltonian U. And the geometry that's behind this gradient flow structure can best be described in terms of this Onsager operator once again. And this takes a very similar form than for linear Markov chains that we just discussed. So it's again a discrete divergence of a discrete gradient weighted by the logarithmic mean of product of measure and transition rate, except that now here the transition rates, they depend on the measured themselves. So they can the mean field equation using this structure can be given a variational characterization. So one can look at the energy dissipation identity, the difference of the free energies, time interval of the square of the speed of the curve with respect to this transport geometry, and the dissipation at time t. And the mean field equation will be the unique minimizer of this dynamics, of this functional. And the nice feature is that this gradient flow structure at the mean field limit is consistent with the one of the particle systems. So we started out with an n particle system, which was a Markov chain on a high dimensional state space, a high dimensional product space. And from the work of Maas and Mielke that we discussed a couple 2 slides ago, this carries a gradient flow structure with respect to discrete transport distance. And one can use the idea of what is called evolutionary gamma convergence to pass to the limit as the number of particles tends to infinity. So precisely whenever the empirical measure converges almost surely to a certain measure m, we can compare kind of this characterizing functional on the level of the particle system with the corresponding functional of the mean field dynamics. And it turns out that the limiting object will be less than the lim_inf of these quantities. So in particular, if we start out with the gradient flow here, so the left-hand side will be 0. Also, the right-hand side needs to be 0. So this allows us to identify the limit. And in particular, gives one way of showing the convergence to the mean field limit and propagation of chaos for such systems. Okay. And there's also a very nice analog of the use of displacement convexity to get control of such systems. If we have information available on our driving functional driving free energy F being strictly convex with respect to geodesics in this discrete transport distance, then one can entail that there's a unique steady state for the dynamics, which is a minimizer of this functional. We have a modified logarithmic Sobolev inequality comparing the reduced free energy to the dissipation of the system. This gives exponential convergence in entropy of the system. We also get exponential contraction in this discrete transport distance and an energy transport inequality comparing transport cost to a square root of the entropy. And this is the precise discrete analog of the celebrated results of Carrillo, McCann, and Villani for continuous Mackin-Vlasov dynamics. Okay.
Yes. I have a question concerning the previous slide, the previous result. So you assume that that F is lambda geodesically convex, but
yes.
So this is something that you can check. You have a check. So this assumption has been verified, I suppose, in a class of.
Yes, for instance, examples that where we can verify this are. For instance, the Curie-Weiss model is a very typical such mean field model, or some certain variants of zero range dynamics where you have jumps, say on the complete graph, and the rate of jump depends on the number of particles present at the initial and final location.
Okay, thanks.
Okay, let me mention a couple of related developments where such Taylor transport geometries have been used in different settings. For instance, this has been applied by myself to jump processes and non-local equations. For instance, to the fractional heat equation, where you have a fractional power of the Laplacian driving the dynamics. there are also similar structures for reaction diffusion systems. So generalizing the picture in two directions. One, that there's multiple components of species with diffusion and potential cross diffusion, and there's also reaction between the different species. There's very interesting work concerning the evolution of dissipative quantum systems, or from a technically related, but from the application point of view, very different angle, a work on optimal transport between not scalar densities, but matrix valued fields, say by Carlin and Maas, Mielke and Mittmann-Zweig, Jen, Giorgio and Tannenbaum. And there are developments for kinetic equations, such as Boltzmann and Landau equations, and for the Katz particle system. There's work by myself that I would like to talk about in the last couple of minutes, and then there's also work by Basile Benedetto Bertini from Rome for linearized inhomogeneous Boltzmann equations, and recent work by Corrido and co-authors for the Landau equation. Okay, so before I maybe Alessandra, let me briefly check the time. I don't know when we precisely started. When should I come to an end?
So you have 5 to 7 minutes left.
Okay. Then okay, let me briefly mention another a recent development which seeks to expand the scope of these gradient flow techniques, and this is the idea of considering generalized gradient flow structures. So let me briefly recall what we've seen so far. If we look at a gradient flow, we've used the energy dissipation identity to characterize the gradient flow as the minimizer of a certain functional, which was the difference of the driving functional at initial and final time, then integral of the speed and of the dissipation. And both speed and dissipation, they were quadratic objects. The speed is quadratic in the time derivative of the curve, and the dissipation is quadratic in the slope of the curve of the functional. More general, one can replace these quadratic functionals by non-quadratic ones, which are convex duals of each other. So one can consider a pair of convex dissipation potentials, R of x and v, and R star of x and v, and they are convex conjugated in the second variable. And then one can consider a similar functional where one replaces the quadratic objects by these convex conjugated objects, plugging in the time derivative of the curve and the differential of the functional. And this, the unique minimizer of this or the minimizer of this will again characterize a certain evolution, which is then a generalized gradient flow. So this draws a lot of motivation from the connection to large deviations, where such functional J's arise as the rate function on the path level. So among many works in this direction, let me cite or pick to cite the work by Mielke, Pelletier, and Renger, where this has been discussed in an abstract setting. And this coming from large deviations in many situations gives rise to, in a natural way, to such nonlinear or non-quadratic gradient flow structures. For instance, for the case of Markov chains that we discussed, the Kolmogorov-Forward equation is the generalized gradient flow of, say, 1/2 the relative entropy if we choose this potential R star to be something like this, sum over the square root of the measures, the rates times a cosine hyperbolic appear. And this, the functional J that one gets in this fashion is precisely the path level large deviation functional for the empirical measure as for independent copies of the Markov chain. Okay, let me spend the last couple of minutes on developing ideas from optimal transport for the Boltzmann equation. So this in a certain direction falls in a in a similar framework, because it's on the one hand it's directly connected to a nice interacting stochastic particle system. On the other hand, it's an evolution equation with non-local effects. So it describes the evolution of a rarefied gas. Time derivative of the density is given by the so-called collision operator. The microscopic picture is that we have particles of the gas colliding, and when they collide, they change their velocities, conserving energy and momentum. And the evolution is in such a way that we have a gain term when two particles collide to produce a particle with velocity v, and a loss term when two particles, or when a particle with velocity v collides with somebody else and changes its velocity. Okay, there's a famous observation already by Boltzmann himself, just termed the H theorem, namely that the entropy is non-increasing along solutions. So the mathematical entropy here with a plus sign is non-increasing. And there's a natural question whether there's maybe some structure hidden behind this that explains this fact in terms of the dynamics is such that it actually wants to decrease the entropy as fast as possible. Okay, this is indeed the case. One can construct a gradient flow structure for this dynamics. And this is not the usual Kantorowicz-Wasserstein geometry, but it needs to take into account the collision process. So it's instructive to see how this works to take a look at the weak formulation of the Boltzmann equation. So we just multiply this by a test function, and then we have here the term coming from the collision operator with the product of ingoing and outgoing velocities. We symmetrize this over exchanging the role of the two incoming ones and symmetrizing between outgoing and incoming. We get kind of an alternating sum of the test function that's denoted by a gradient bar. And then one can again define a formal Riemannian structure in terms of such an operator K, which takes this alternating sum and multiplies it with a weight depending on the density. And there again, the logarithmic mean shows up mysteriously, this time evaluated on the product of of the two incoming and of the two outgoing velocities. And then one can indeed describe the evolution as a gradient flow of the Boltzmann entropy in this geometry. And this formal geometry gives rise to a transport distance that models this collision process between the particles. Okay, let me be very brief on this and basically let this be the last slide. So one can use this structure to give a variational characterization of the Boltzmann equation in the fashion we've seen before. It will be the unique, or it will be solutions to the Boltzmann equation will coincide with minimizers of the energy dissipation functional, difference of the entropies, integral of the dissipation, and integral of the speed. And in a similar fashion, more with an eye towards large deviations, one also can construct a generalized gradient flow structure for this dynamics. And one crucial feature about this is that it allows to have an approach to the CATS program using the rigidity of gradient flows. So starting from CATS particle system, which I'm afraid we won't have time to talk about, and exploiting the fact that this particle system as a Markov chain has a gradient flow structure, and passing to the limit in this gradient flow structure to identify the limiting curve as the solution to the Boltzmann equation. So I already mentioned the related works in this direction from colleagues from Rome and London. So let me wrap up by saying that we've seen the use of tailor-made transport geometries on the space of probability measures allows to have gradient flow characterizations for a large class of stochastic systems with various types of interactions, and they allow to port ideas and powerful tools from optimal transport theory to these settings, and this can yield very strong control on the stochastic dynamics. And a big benefit of this is also that this provides an overarching structure that can be exploited in limit passages, say passing to a mean field limit, passing to scaling limits, passing to a limit from discrete to a continuum, and there might be other circumstances. Okay, so this is all I wanted to tell you. Thanks for your attention, and I'm very much looking forward to questions.
Thank you very much. So I'll now invite everyone to unmute themselves so that we can thank Matthias for his talk. And if you have any questions, there are a few options. You can either type your question into the chat or you can raise your hand and we'll invite you to unmute yourself. So we have one question in the chat so far. It says, how are psi and psi star related?
Okay, let me swap back there. Sorry, here. Okay. In particular for the on this slide, I guess.
Yes.
Okay, so here again, the psi and the psi star are convex duals of each other.
Déjà transform?
Yes.
Thank you.
Actually, maybe I can ask, given you're on that slide, I presume it's just a little typo, is it, where one of the FTs should be F0, is that right?
Yes, exactly. So I'm sorry, the second one should be F0.
Okay, thanks.
Thanks.
Okay, are there some other questions?
I have a question. So it's because, okay, having the slides, okay, I also given the link. So just, it concerns the last slide, the one that you have not commented. So okay. I'm curious because at the end you mentioned discuss a program and there is this, so you mentioned quantitative results. So what do you mean? Can you
okay, there's, so what I did not have a chance to discuss was just a qualitative convergence result and propagation of chaos result that comes out of this gradient flow structure as a byproduct. There are, so I'm not claiming, or I didn't say nothing, but I'm not claiming that this is a new result. This is in fact very old, going back to Snitman. So the point is that this is a nice and natural new angle of attack on such kind of problems. There are even much more refined quantitative results, say giving error estimates in, say, in Wasserstein distance for the convergence of the empirical measure of the Katz process to the limiting Boltzmann equation. And there's also work, recent work by Carapatoso, who gives quantitative estimates on the entropic propagation of chaos. So how fast the normalized entropy of the particle system converges to the entropy of the limiting solution.
But do you have, are there quantitative results also for the, similar quantitative results for the Boltzmann model, Boltzmann equation?
So the ones I mentioned here are for the Katz system and the Boltzmann equation.
Okay. Okay.
And you return to the Boltzmann. What is U in this equation? U capital in Boltzmann equation, yes. Invariation and formulation.
Okay.
Yes, U. What is U?
Here, U is the in some sense the generalized momentum. So this, if we go back here, if okay, so this is a so the associated transport distance comes from a dynamic minimization problem, where you can think of this u as prescribing the rate at which collisions happen between the particles, and then what one minimizes is the square of this rate divided by some function of the density. This is what takes the role of the momentum in the usual Wasserstein distance.
Thank you.
Okay, are there any? Oh, we have another question in the chat. It says, might be naive, but speaking of Boltzmann, does the kinetic Fokker-Planck equation have gradient flow structure?
Okay, so the Fokker-Planck equation, of course, has a gradient flow structure with respect to usual Wasserstein distance. The kinetic Fokker-Planck equation, there's also work on variational characterizations of this, but it's not a pure gradient flow structure, but kind of a mixture of dissipative gradient flow type dynamics and conservative Hamiltonian dynamics. So this, in some communities, that this goes under the name of generic systems combining these two types of effects.
Okay, thank you. I'm not seeing any further questions, so I think in that case it's maybe a good time to. Oh no, one question has just come up. Does the gradient flow approach lend itself to some quantitative propagation of chaos results and convergence?
That's an interesting question. I would expect that something like this should be possible. I mean, quantifying the gamma convergence of the functionals involved. A challenging part of such a program is controlling, for instance, the quantitatively the convergence of the transport cost that's involved. And yeah, we will hear much more about this in the upcoming talk of Jan, where we're in a different setting. Such convergence results are available.
Okay, thank you. I think we probably should stop now, and so we'll resume again at 5 past the hour for the second talk. And in the meantime, I'll just unmute everyone once more just to thank Matthias. Okay, so we'll resume again at 5 past the hour if people would like to go and grab themselves a coffee.
But is Jan, Amanda, is Jan here?
Yes, I'm here. Hi.
Because hi, Jan. I didn't see you in the list of participants.
Yeah, I arrived towards the end of the talk, so I'm sorry for creating this stressful situation, but I'm glad I'm here.
No, it was everything okay. So participants didn't know.
Okay, very good. This part is cut out anyway from right.
I hope everything is okay now.
Yeah. No, it's all fine. Thanks.
Okay. So I make you host.
Okay, very good. Yes.
So that we can. So I have to find your name in the list. I don't see Jan. Maybe Maas. How do you? Sorry.
Yeah, Maas. It's my.
It's there. Yeah.
Okay. I don't see in my list.
If you just type it into the participant bar, there's a search. Just type it; it comes up.
Okay. Thanks. Okay, make host. Okay, now you are host.
Okay, so I should be able to share, I guess.
Yes.
Should I try?
Yes. Okay.
You see something?
Yep, that looks good. Yeah. Do you want to try and move between slides?
Yes. Let me arrange my screen. Oh. Does it work?
Yep, that looks great.
Oh. Hi, does it work?
Yes.
Okay, so I think my sound was gone for a second, but
Sorry, but do you have to? Okay, don't worry.
You see another slide now?
Yes, but do you have to? Sorry, because I was reading the chat. Do you have to? Do you want to write something to check or no?
Okay, to write. Yes, that's a good idea. I think it should work.
Okay,
perfect.
Yes. Okay, very good.
Thanks. Okay, we're still 2 minutes if you need to relax.
Okay, sure.
Jan,
Yes.
have you sent the slides?
I didn't, because actually I'm going to write live.
Perfect.
Yes, so there's something prepared, but most of it I will actually do right now. So therefore I didn't send something in advance.
Okay.
I like Blackboard style talks, but it's hard these days.
You are brave. Some 1 minute. Okay, I think it's time to start again. So first, an announcement. So just to recall that next week we will have the talks of Sylvie Mellard and Kiviet Tran. So more biology, okay, probability. So now, so it's a pleasure to have here Jan Maas, who will talk about optimal transport from discrete to continuous. So please.
Thank you very much. Thanks for the kind introduction, and also thanks to all the organizers for the invitation. It's a great initiative, and it's nice to be able to see some people online, even though, of course, it would be much better to meet all in person. Okay, so I would like to continue with the second part of today's session, following up on Matthias's work. And I would like to speak about a series of works with different people, including Matthias, also Nicola Gili, Peter Gladbach, and Eva Kopfer, and Lorenzo Portinale. Okay, yeah, so let me start with a sort of a brief recap, which kind of overlaps a little bit with Matthias's talk. But we're interested in studying optimal transport for various reasons. These are important sort of distances between probability measures, and sort of a crucial role is played by these Kantor-Rovich-Wasserstein metrics, which are defined for any p. And what is the definition of this Wasserstein p metric? Well, there are various ways to look at it, but sort of the probabilistic description is that you look for random variables x and y, where x has distribution mu naught, y has distribution mu 1, and you minimize the pth moment of x minus y. So this gives you this is the Wasserstein distance to the power p, and this gives you a metric on the space of probability measures for every parameter p. And right, so this is sort of the more analytic way to write down the same thing. So you're looking for all probability measures on the product space. What you're minimizing is the integral of x minus y to the p, and you minimize overall probability measures with given marginals mu naught and mu 1. Okay, so that's the classical Monge-Kantorowicz formulation of the optimal transport problem. But as we have just seen in Matthias's lecture, it's actually very fruitful to look at this optimal transport problem from a slightly more dynamical point of view by introducing a time parameter. Yeah, so what you do is you actually regard your probability distributions as a cloud of particles, say here located at time 0. And you're also given a distribution of particles at time 1, given by this measure mu 1. And instead of just looking for optimal couplings between the two measures, you're actually considering curves in the space of probability measures, which interpolate between these given boundary measures. And what you would like to do is you would like to again consider some minimization problem. And what you would like to do is you would like to minimize the total kinetic energy. So you consider the vector field Vt, which is the velocity vector field, transporting my particles. And then this Benamou-Brenier formula tells you that for p equals to 2, if you look at the quadratic Wasserstein distance, you can find it by minimizing this quantity. So the integral over space-time of the squared velocity against the mass. This is, of course, the kinetic energy. And you optimize over all solutions to the continuity equation with given boundary conditions, mu naught and mu 1. Okay, and a remarkable thing is that this dynamical point of view is equivalent to this more traditional Monge-Kantorowicz picture that you saw in the previous slide. Okay, well, and as we have seen, one of the interesting features of this description is that actually you can regard this formula, at least formally, as the formula for Riemannian distance on the space of probability measures. And this point of view was sort of introduced by Felix Otto around 2000, and it has become really the starting point for many developments. And you can really do some sort of analysis on the Wasserstein space with connections to PDEs, to curvature, and sort of analysis in metric measure spaces. Okay, so that's sort of the equivalence between static and dynamical optimal transport. And well, sort of one of the highlights in this story is then the fact that you can indeed describe some diffusion equations as gradient flows in the space of probability measures P2 over Rd with respect to this Wasserstein metric. And the prime example is given by the situation in which your driving functional is the Boltzmann entropy. So h of mu is the integral of rho log rho, where rho is the density of mu with respect to the Lebesgue measure. And then the famous result by Jordan, Kindler, Otto tells you that the diffusion equation or the heat equation, so dt mu equals Laplacian mu, is in fact a gradient flow in the space of probability measures, where the driving functional is the Boltzmann entropy. And the relevant geometry in this gradient flow description is given by this Wasserstein metric from optimal transport. So the metric W2 defined on the previous slide. Okay, so loosely speaking, it tells you that what diffusion does is it tries to increase the entropy as fast as it can, while simultaneously not move too much with respect to this Wasserstein metric. Okay, so this is a key result in the story. It has many extensions to also beyond sort of the classical situation of Rn. It extends to Riemannian manifolds and to geodesic spaces in great generality. But if you want to include the discrete setup, then actually some modifications turn out to be necessary. So sort of the starting point of what I would like to discuss in this second talk is also what Matthias already mentioned, is that you can extend these ideas to the setting of discrete stochastic dynamics. And here the setup is very general. So you just consider a Markov chain, so an irreducible continuous time Markov chain on a finite side X. Or if you want a countable set, so the ideas carry over with some modifications to the countable setting. And it's characterized by its transition rates, which I denote by QXY. So what is crucial in this gradient flow description is actually the reversibility. So that's that you assume that the unique invariant measure, which I call pi, it satisfies this detailed balance condition. So there's a symmetry condition involving the transition rates and the stationary measure, which is the usual reversibility condition. And this condition is actually actually it turns out to be necessary and sufficient for obtaining a gradient flow structure. Right, and sort of the analog of the JKO theorem in this discrete setup is then given sort of by the natural discrete heat equation, which is the Kolmogorov forward equation for the Markov chain. So given by this kind of this evolution equation on the space of measures on my finite set X. And the driving functional is now the relative entropy with respect to the stationary measure pi. So for a probability measure M, given by the usual formula, where you have the analog of rho log rho, but now discrete. Okay, and then the theorem, which is the discrete JKO theorem, is that this Kolmogorov forward equation is in fact the gradient flow of the relative entropy with respect to a certain discrete dynamical transport metric, which I denote by this curly W. Okay, yeah, and the interesting thing is sort of that this metric is not a Wasserstein metric. So while the Wasserstein metrics are really sort of the right objects to use if you're interested in continuous setups, right? In very great generality, it turns out that if you want to do the discrete counterpart of this theory, then you really have to work with different metrics. Okay. And well, these metrics, they're defined over here. So let me recall the setup for this discrete dynamical transport metrics. They're really defined by sort of an analog of this dynamical formulation that we saw just before. So what you want to look at is also a continuity equation in the discrete setup. So we say that the pair M and J, where M is a curve in the space of probability measures, and J is a time-dependent function, which is defined on the edges of your graph, and we assume it to be asymmetric, because we think about it as being a flux through an edge. So a flux in one direction is sort of minus the same flux in the opposite direction. Well, and then the discrete continuity equation is this very simple kind of ordinary differential equation, which is just Kirchhoff's law. Meaning sort of the change of mass at a given vertex is equal to the sum of the fluxes over all neighboring, well, through all edges which are sort of incident to this vertex. And so that's the discrete continuity equation. And let me stress that sort of we always assume that this J is in fact antisymmetric. Yeah, so this can be a flux in one direction or sort of minus the flux in the other direction. So it's a net flux through through an edge. Okay, so this is sort of the discrete continuity equation. And then these dynamical optimal transport metrics, they are defined by some sort of analogs of this Benamou-Brunier formula. So if I have a pair of measures, M0 and M1, probability measures defined on this set of vertices of my graph, then, well, the squared distance, squared transport distance, is obtained by this minimization problem, where again you integrate over space-time. So in this case, it corresponds to integrating in time, summing over all the edges of your graph. And then what you're actually integrating is actually again sort of an analog of a discrete kinetic energy, or sort of an analog of a kinetic energy. And that means that it's like a momentum square divided by a mass. So in the numerator, we indeed have this momentum vector field through the edge, which is square. And in the denominator, you need a little twist in the discrete setup, because you want to divide by the mass which sort of flows through the edge. But of course, there's a different mass at, say, the left end point and a different mass at the right end point. So it's natural to consider actually some sort of averages between the mass at the given endpoints of your edge. And here you already have a choice to make. So in the discrete setup, there's not really one canonical way to do it, but sort of the non-locality of the discrete situation creates sort of multiple choices. But it turns out that actually to have this gradient flow structure, there's actually one sort of distinguished choice, and this is this logarithmic mean. So this function lambda here is defined as the logarithmic mean of these weighted masses at the left and at the right. So you can write it here in this integral form, where you see that it's sort of an average of the two. But you can also view it as these different quotients between a minus b and log a minus log b. Okay, so that is sort of the discrete transport metric defined by a minimization problem a la Benamou-Brunier, but with a little twist given by this logarithmic mean, which you don't see in the continuous setup. Okay, so well, this was also already pointed out in Matthias's talk. So why this logarithmic mean? So this logarithmic mean actually shows up because you want to write your heat equation or your Kolmogorov-Forward equation. You would like to write it as a transport equation. And the same you can do also in the continuous setting. You can write your heat equation as a transport equation. But if you do it, you actually would like to write sort of the gradient of your density rho. You would like to write it as rho times grad of log rho. And that's actually something that you would like to do in the discrete case as well, but it doesn't quite work because there's not a chain rule for discrete derivatives. And the choice of this logarithmic mean is really motivated by the fact that it provides some sort of analog of a discrete chain rule for this logarithm, as you can see by looking at this expression over here. Okay, so that's the sort of the main player of this talk, so the optimal transport metric in a discrete setting. Okay, so yeah, so what I'm interested in this part of the presentation is actually, so what happens sort of if we pass to the limit from discrete to continuous. So we have seen that this is sort of a natural analog of a transport metric, but it's not a Wasserstein metric. So it's sort of natural to ask, how do these metrics actually behave if you pass in some sort of scaling limits from discrete to continuous. Okay, so let me discuss this sort of the story around this question. And sort of the starting point is really kind of the simplest setting that you might try to look at, and that's the situation where your discrete system is just like a square lattice, say the Cartesian grid. So for simplicity, let's just look at this in a compact setting. So we look at the discrete torus given over here, where we have just this periodic mesh, which is just a square grid, and the neighboring vertices there have distance epsilon from each other. And now what we would like to do is we would like to define sort of the transport metric on this lattice associated to sort of the natural discrete Laplacian on the grid. We would like to rescale it, and the question is what comes out in the limit. So here's again sort of the formula of the discrete transport metric. So for each epsilon, it's given by exactly the same formula that we saw before. So you minimize sort of the total transport cost. Actually, I forgot to write the time integral here. So let me squeeze that in. So you minimize the integral in time, the sum over edges, and then there's again sort of the j squared divided by the mass, so the kinetic energy. And integrate in time over all solutions to the continuity equation. Okay, and well, it turns out that if you want to obtain some non-trivial continuous limit, then the natural scaling that you need to put here in front is actually epsilon square. Why the epsilon square? Well, it's because this if you discretize sort of a continuous diffusion equation, you will find that these masses here, they are of the order epsilon to the d, right? So they represent volumes. So the length is epsilon, the volume is epsilon to the d. So the denominator scales like epsilon to the d. The vector field j here in the numerator scales like epsilon to the d minus 1, because it's like a flux through an interface. Yeah, and then you sum over order epsilon to the minus d instances. So if you want to get something non-trivial in the limit, you need to multiply by epsilon squared. Okay, so that's sort of the simplest setup. And well, the result that we have in this particular situation was obtained a few years ago in a paper with Nicola Gili. And well, fortunately, things are kind of nice in the setup. So what we showed is that if you look at the space of probability measures over this torus with sort of length epsilon, and we look at the associated transport metric, then this converges as epsilon tends to 0 to the space of probability measures over the continuous torus, and out with the Wasserstein metric W2. So sort of what you would expect, I guess. So you get the Wasserstein 2 metric in the limit. Still, I should also emphasize that this Wasserstein metric here in the limit, it's really the Wasserstein metric with respect to the Euclidean distance on the underlying space. So if you pass to the limit, actually what gets sort of lost is the is sort of this L1 type structure of your discrete network. But in the limit, you really get sort of the Wasserstein 2 over Euclidean space.
Sorry, Jan, a question. It's also in the chat. So are you taking here Qxy equal to 1? So the question in the chat is, where is the transition matrix in the definition of metric?
Yeah, thank you very much. Indeed, so I'm taking the transition rates all equal. So I'm really considering the simple spatial situation, the simple random walk on the on this lattice. Yes, okay. Thank you. Okay, so this is indeed with respect to the Euclidean metric on the underlying space. Yeah, what I should also stress is sort of that you see there's this logarithmic mean, this lambda in the definition of your transport metric, but actually the result holds for any mean. So you can replace this logarithmic mean by the arithmetic mean, the geometric mean, harmonic mean, or pick your favorite, and they will all converge to the same Wasserstein metric. Okay, so that's sort of the simplest kind of sanity check, I would say. So in the basic situation of this grid, we indeed get the convergence that we might expect. So let me move on to another example where things actually are not as straightforward as you might guess. So we have seen that in the very symmetric situation of this Cartesian grid, we actually do get the convergence. Let's now consider again. So let's consider a simple example in which my underlying space is just a one-dimensional lattice. Very simple. Right, and so there are two parameters in this model. There's a parameter epsilon, and epsilon is just sort of the represents the distance between points. So the distance between consecutive points is actually epsilon over 2. I do this over a unit interval with periodic boundary conditions. So again on the torus, and I just assume for simplicity that epsilon is 1 over an integer, such that everything works out. And then I'm going to consider like simple random walk on this one-dimensional lattice, but with a twist. And the twist is that sort of you are going to alternate fast jumps and slow jumps. So I color my points red and green in an alternating way. And I'm going to jump from green points with a different rate than I'm going to jump from the red points. And the rates are also written over here. So the rates, they scale in terms of epsilon, like 1 over epsilon square. It's the usual diffusive scaling. But I put a prefactor, proportional to 1 over 1 minus r in front of the red points. And I put a prefactor 1 over r for the green points. Yeah. So if r is small, actually it means that I'm going to move faster from the green points, and I'm going to move slower from the red points. Okay, so this is a very simple one-dimensional model. And well, you can of course easily write down the stationary distribution. So this is a reversible Markov chain. The invariant measure is given by this explicit formula. So it's sort of inversely proportional to the rates. So if r is small, you're going to spend little time proportional to r at the green points, and you're going to spend time proportional to 1 minus r at the red points. Okay. Now what we know is that sort of for each r, this Kolmogorov forward equation, is the gradient flow of the relative entropy. So the relative entropy with respect to this stationary measure pi epsilon r. With respect to some discrete transport metric, which is given by the formula that I gave you before, and it depends also on the parameters epsilon and r. Okay, so now what we would like to do is we would like to fix r and pass to the limit in epsilon. So we sort of keep the asymmetry, but or it's not an asymmetry, but sort of we keep the sort of the difference in the rates, but we would like to pass to sort of the continuous limit. So if I pass to the limit epsilon tends to 0, then things are set up in such a way that this Kolmogorov forward equation actually converges to the usual heat equation. dt rho equals Laplacian rho in one dimension, of course. And in particular, it really converges to the same heat equation for any value of r. Right. So this the scaling is such that sort of no matter what your parameter r is, the simple random walk with these rates will converge to the Brownian motion with the same speed, not depending on r. Okay, and we would know that sort of this heat equation is the gradient flow, well, of this integral rho log rho, right, the Boltzmann entropy, in the Wasserstein space. Yeah, so with respect to the transport metric W2. Well, it's sort of easy to see to the Boltzmann entropy in the limit for any value of r. So therefore, it's of course very natural to suspect that also here you would have the convergence. To the Wasserstein metric in the limit. However, so what we show is that this is not true. So this turns out to be false. So what we can show in this particular example is that these metrics, so W epsilon r, they converge as epsilon tends to 0 to the Wasserstein metric, but we have a different prefactor depending on r. And this prefactor is actually kind of explicit. Let me just write it down. Kr is obtained by minimizing over all alpha in 0, 1. The logarithmic mean of 1 minus alpha, 1 minus r, alpha divided by r. And this guy to the power minus 1/2. So what you see here is that the convergence of the transport metric is actually not determined by the convergence of the associated gradient flow equation. Yeah, so the behavior of the transport metric is more complicated somehow. Okay. Yeah, and what I would like to explain in the rest of the talk is also where this comes from, right? And also gives you actually a theorem in greater generality about what's happening in this situation. Sort of intuitively, sort of if I can already say something. So so what's going to happen if you do sort of the optimal transport in the discrete setup here is that the optimal discrete transport is sort of obtained by approximating the continuous transport, but in such a way that you put a lot of mass in the green points and little mass in the red points. So the optimal transport will actually create sort of artificial oscillations, which actually make the transport cheaper than you would expect based on the expected continuous limit. So there's sort of microstructure in the model which actually can be exploited by the transport.
Jan, sorry, there is a participant who would like to ask you a question, so please.
Yeah, thank you. So the formula there for this effective coefficient, is it possible to interpret that as having two species in this model, and then this is some natural interpolation between a weighted interpolant?
I'm not sure whether it's really two species, but I will give sort of a more general formula later on, where I think it will be a bit more clear where this actually comes from. So let me postpone the answer to this question.
Okay, super.
Yeah.
Mm-hmm.
Okay, thanks.
Okay, thanks. Okay, so but in any case, this example shows that things are sort of not quite as intuitive as one might expect a priori. Okay, so let me move to a slightly more general setup, which in which this example fits, and that's sort of the general setup of ZD periodic graphs. So the situation is sort of given as follows. So we start off with a graph XE, which is a graph in the continuum in RD, which is ZD periodic. So for instance, the one which is drawn in this in this picture here. Yeah, so it extends sort of indefinitely. And so it's a ZD periodic graph. Okay, so then we would like sort of to actually sort of zoom out and sort of again pass to sort of a scaling limit of transport in this kind of ZD periodic graphs. So to do that, we actually define a sequence of rescaled graphs and E epsilon, and they are defined by rescaling the graph. Yeah, so so initially these were sort of blocks of unit length, but now I'm rescaling things such that these lengths are actually of order epsilon. And then what we do is actually we also prefer to work with sort of compact settings. So we actually wrap the graph around the torus. And so what you can do if sort of epsilon is 1 divided by an integer. Yeah, so we're looking at sort of periodic graphs on the torus, which arise from sort of these ZD periodic graphs. And we would like to understand what happens in the limit as epsilon tends to 0. Okay, so here's sort of the definition of the transport problem in this setup. So given two measures, M0 and M1, which are again the boundary values, probability measures in my epsilon graph, I define this transport cost C epsilon by sort of the usual minimization problem, which we have seen a couple of times. So I integrate in space. I sum over all the edges in my graph, and then I consider a cost function. And actually, I wrote it now slightly more general because our result is slightly more general than what we saw before. So before I had sort of j squared divided by a logarithmic mean of the mass at the edges, but you can actually, so there's some function cxy depending on the mass at x, the mass at y, and the sort of the momentum vector field in the continuity equation at the edge x, y. And so think about this j squared divided by logarithmic mean as one particular example. Yeah. But what we allow here is these costs to be arbitrary lower semi-continuous and convex functions satisfying some growth conditions, which are periodic. So they respect sort of the periodicity of the lattice or of the graph. And then you are going to minimize this again over all solutions to the continuity equation as before. But of course, you would like to rescale things. And the way how this rescaling is done is as follows. So as I mentioned, sort of these masses, they scale like volumes. So they scale like epsilon to the power d. So you would like to divide by epsilon to the power d. For the mass at x, same for the mass at y. Whereas these momentum vector fields, so these fluxes through the edges, they scale like areas, like surface areas. Okay? So they scale like epsilon to the d minus 1, so I divide by epsilon to the d minus 1. And then, well, the number of edges is proportional to epsilon to the minus 1 over sort of epsilon to the minus d. So to get something at order 1, it's sort of natural to multiply by epsilon to the d. And so this is my rescaled cost in the epsilon periodic lattice. Yeah, and of course the example from the previous slide is just a particular case in one dimension. Okay, so maybe just a comment actually. So we are considering these graphs. They're ZD periodic, and you can think about them in two ways. So either you think about them really as sort of graphs embedded into a continuous space, where each of your vertices correspond to a point in Euclidean space, or you can just also think sort of about them more abstractly, namely to each cube in your space, you associate a finite number of points. So what I'm trying to say is that sort of the exact location of your points in your graph actually is irrelevant, because the sort of cost function, it doesn't appear in the cost function here. But for intuition, it's maybe easiest to think about sort of an embedded graph in space. a question, I think.
Yes, there is a question.
Yeah, thanks. Just quickly, I was trying to comprehend where the metric, the underlying Euclidean metric, comes in here. So you just made that comment. What about these systems on hyperbolic spaces?
Okay. So I will show you where sort of the Euclidean kind of continuous setting appears. So far, we didn't do anything on sort of more complicated spaces, but of course, it will be interesting.
Just with the graph structure, you have the feeling that you could basically capture all of those and then just detect the differences as you go.
Yeah, of course, one could ask similar questions in more complicated situations. Yeah, that's right.
Yeah, super.
Okay, so this is sort of the setup, and then the question that we're interested in is of course the following. So what happens to this cost? So C epsilon of mu1 and mu0. So what happens to this quantity in the limit if you take sort of sequence of measures m naught epsilon converging to so weakly converging to m naught, and m1 epsilon weakly converging to m1 to mu1. Okay, so here's the result, which I'm going to write down. For your convenience, I recalled sort of the formula of the cost at the discrete level. So this is just the same formula copied from the previous slide. So the cost at the epsilon level, and the result is as follows. So take any measures at the discrete level. Suppose that they converge to some measures in the continuum after embedding. Then what we show is the following. Sort of this transport cost, C epsilon, between m naught epsilon, m1 epsilon. This converges to something which is also expressed by a minimization problem. So this is the infimum, integral 0, 1, so integral in time, integral in space. And now there's some function which I call C-hom, so sort of a homogenized cost function, depending on rho tx, jtx, dx, dt, where I minimize over all solutions to the continuity equation, really the continuous continuity equation. So dt rho plus divergence j equals 0 with the given boundary conditions. Yeah, so rho naught is rho naught, and rho 1 is equal to rho 1. Yeah. So what it tells you is that indeed these discrete transport metrics in this periodic setting, they converge after rescaling to something of this form, which is just sort of the dynamical formulation of a continuous transport problem. With some function here, C-hom, which is a homogenized cost function, and I have to tell you what it is. And this is actually something that sort of will take into account sort of the geometry of your sort of the local structure of your graph. And let me give you the formula where C-hom is defined as follows. So what you do is, well, I want to define a C-hom, so I would like to fix some rho. So it's just a positive number, non-negative number, which sort of represents sort of the density locally, and a vector in RD, which represents a momentum vector. And I would like to define what is the homogenized cost of rho comma g. Well, this is given by a cell problem. Yeah, so this is given by minimizing sort of this transport cost, which is the same really as before, where you really minimize over a single unit of periodicity. And so you really sum in your ZD periodic lattice, you sum over all the vertices which lie in the unit cube. You sum over sort of all the neighboring vertices. And then you minimize this, this cost over what I call the representatives of rho J. So this depends on M and J, and these are representatives. So what are these? Let me write it down. So these representatives of rho and J, they are given by the following expression. So these are all pairs, M and J, where M is a function on X to R plus, which is ZD periodic. J is a function on the edges, so a vector field. So again, ZD periodic and antisymmetric as usual. And also divergence free. So at every vertex, sort of the sum of the fluxes equals 0. And they represent rho and J in the following sense. So if I compute M of X, and I sum over all the vertices in a single cell, so I integrate over the vertices in my graph intersected with the unit cell, this should sum up to rho. And similarly, if I sum over all the vertices where X belongs to a unit cell, and if I sum sort of the following quantity, so I look at these vector fields, so J XY, and I multiply them with the vector Y minus X. So Y minus X, these are really sort of points in Euclidean space. Then it should be equal to J. So the set of representatives of rho and J, these are given by sort of ZD periodic functions on the vertices of my graph, ZD periodic functions on the edges of my graph, and they represent rho and J in the sense sort of that the total mass equals rho here, and so the effective flux equals J. Okay, so that's the definition of the cell problem, which determines the homogenized cost. Let me maybe illustrate this by one example to make this a bit clear. So here's again the same graph, right? And I zoomed in onto a single cell, and I would like to give you sort of what is the representative of this pair rho J, where rho equals 6, so the density equals 6, and this momentum vector is the vector 3, 1. So a possible representative is obtained as follows. So I would like to put sort of total mass 6 into my cube. So I assign mass 2, 3, 1, for instance, here to the vertices, and I do this periodically. And I would also like to represent this this vector J, and for this purpose I put sort of fluxes through the edges. So I put here, let me put them in blue. I put here flux 2. I put here 1. I put here 3. I put here 3. I put here 3. I put here 4. I put here 5, and it's periodic. So here's again 1. Here's again 2. So what you can check is that then sort of that the sum of the fluxes through each node equals 0. So that means that it's divergence free. And moreover, sort of the effective flux is given by this vector 3, 1. And one way to check it is for instance by sort of looking at each vertical slice, sort of the amount of mass which flows through it is exactly given by 3, which you see here, for instance. And similarly, sort of each if you look at all these horizontal slices, then the flux through it is actually given by 1, sort of in the downward direction. So this is a so this function, which I sort of try to indicate here, is actually a representative of these of rho equals 6 and j equals 3, 1.
Sorry, Jan, just a question, because maybe there is some confusion, so it's not clear to everybody. So the question in the chat is, what is the size of the torus? So what is the size of the cell, periodic cells, and the size of the torus? This was the question, just. Right,
okay. Yes, okay. So what I'm considering is I'm considering sort of the I consider the continuous torus of scale 1, of unit scale, and on this continuous torus I have sort of these embedded graphs, which are periodic where the unit of periodicity is given by epsilon. Yeah, so they repeat themselves each epsilon.
Okay,
and then I would.
Yes. But when you introduce the representative, you write a 0, 1 to D as
okay.
cell is.
Exactly. So in the formula for the representatives, this is not at the epsilon level, but the representatives, this is really at the level of my original ZD periodic graph. Yeah. So the cost, so the sort of the homogenized cost function, I can read off by sort of looking at the original graph at scale 1. So there's no epsilon in this definition of the representatives.
Okay, I think it should be clear now. Thanks.
Okay, thanks for that question.
Thank you.
Okay. Okay, so this is sort of the main theorem, which sort of answers what happens in the for dynamical optimal transport, discrete dynamical transport in the setting of periodic graphs. And you see this is a result for general costs, but we can actually, if you specialize to this situation, which is most relevant for the gradient flows, where your cost is of the form momentum square divided by logarithmic mean, then what you can actually show is that you converge always to a Wasserstein metric, a Wasserstein 2, but it's a Wasserstein 2 with respect to some non-trivial norm on the Euclidean space. Yeah, it's always Wasserstein 2, but it's not Wasserstein 2 with respect to the Euclidean metric, but it's Wasserstein 2 with respect to some norm, which is sort of determined again by the cell formula, and it's really a consequence of sort of this local inhomogeneities that you have in your periodic graph. Okay, so I think that's probably a good point to wrap this up. So you see that sort of these dynamical transport metrics, they arise very naturally in these gradient flow descriptions, but the gradient flow description does not tell you automatically what happens if you're interested sort of in limiting behavior, sort of large scale behavior of these discrete transport metrics. Okay, thank you very much.
Okay, thanks a lot. So first of all, I would invite everyone to unmute so that we can now together thank Jan for this very nice talk. So we have some time for question. Okay, there is a question in the chat. Okay, was the homogenization result already known in the continuum with a periodic metric? And what about a random instead periodic?
Okay, so those are good questions. Okay, so concerning the first question, I'm not aware of this result. So not that I know. Concerning the second question, that's of course very natural and something that we're also very interested in. So we have some ideas, but I think it's too early to report any results in this direction. But of course, it's very interesting to see what happens on random networks.
Okay, thanks. Is there any other question?
I have a question, Jan. If that formula that you presented for the one-dimensional structure, this is the n-dimensional analog, yeah?
Yes.
So are there any representative formulas that give you, for example, in 2D, an analog of that one-dimensional formula?
Yeah. So indeed. So this formula, which is still displayed right now, so that sort of this contains this one-dimensional example. In one-dimensional case, sort of the situation is particularly simple, since this minimization over these vector fields actually disappears. So this formula that I showed you is really a result of sort of optimizing the distribution of the mass, and you have no freedom in choosing the vector field. So if you, so a two-dimensional analog would, for instance, look at sort of a trivial graph again, which is just ZD, but put now some different rates than what I put before. Then you could also, I mean, so if you just have a single point, or well, let me set it right. So in that particular case, also there's sort of no flexibility in sort of optimizing the fluxes. So you would get sort of also a slightly simpler formula, which sort of resembles the one-dimensional situation, where you only have sort of an optimization over masses.
Yeah, I guess I was trying to comprehend sort of how you could generate anisotropy, and also, in some sense, as you were sort of indicating, does the shape of the graph matter? The actual location of the points? Is there any geometrical content in, let's say, the shape of the points one to another?
Right. So the local graph structure indeed matters. So you it's very rare actually that you will converge to the Wasserstein metric with respect to the Euclidean distance. So if you would look sort of beyond the periodic setting, but you would just look, say, at some kind of Voronoi discretization of your Euclidean space, then it will almost never converge. So the resulting metric will almost never converge to the usual Wasserstein metric, unless you have some very specific symmetries. So for instance, on the triangular lattice in 2D or the hexagonal lattice, it will converge. But almost any other situation, there's some non-trivial limit, because you can sort of optimize your mass locally in a clever way and create a cheaper transport at the discrete level than you would expect from the continuous limit.
Yeah, thanks, Jan. Super talk.
Okay, I think I saw Daniel Adams, but he has disappeared. Maybe he wanted to ask a question.
I was just wondering, is there any, what's the significance of these discrete results beyond like the theoretical level? Can you use these JKO schemes to simulate these processes? And if so, can you regularize these new metrics?
Can you? What's the question?
Have you looked into regularizing these new costs, adding some regularization into your costs?
So if you're already asking for, you're asking for like computing sort of really computational results, right? Yeah, I mean,
well, in the continuous case, the results where you regularize your Wasserstein metric with some entropy. I'm wondering if similar is done here.
Yeah, so there's lots of activity sort of in sort of the more computational side of Wasserstein metrics, and there's been a lot of progress. And as you say, sort of one of the key insights is that you can use some entropic regularization to compute sort of these continuous metrics, and then use some Sinkhorn algorithm for computations. At the discrete level, for these dynamical transport metrics, it doesn't seem to be the case that you can easily apply sort of the same idea. So there's sort of some algebraic miracle happening with Sinkhorn, if classical Wasserstein metric, which somewhat doesn't happen in the discrete case. So there has been work also by Matthias Erbar and Martin Room, for instance, on computing these dynamical transport metrics. But there's not such a nice trick as Sinkhorn, which we have for the continuous Wasserstein.
Thank you.
Okay, thanks. So there is a question in the chat. What are some other sufficient conditions? Sorry, it is moved. That you get about the convergence of matrix entropy and gradient flows. Is it clear, Jan?
Sorry,
Sorry, what was the question clear?
No, I misunderstood the question. So the question was what?
Whether there are some sufficient conditions to get both convergence of your metrics and the entropy and the gradient flows, like aside from like some lambda convexity, like as you nicely explained that your convergence of your metrics don't actually get you convergence of the gradient flows or vice versa. But what are some other non-trivial conditions to truly get actually convergence of all three at the same time, which of course should be quite strong?
Right. Yeah, so it depends a little bit on the context in which you ask this kind of question, but you know, you get a lot of stability as soon as there is sort of some uniform convexity around.
Yeah.
So if you have sort of geodesic convexity along your approximations, so or at least some lower bound on the Hessian, which you can control uniformly, then things turn out to be very stable. And then the things that you ask for, they would hold true. If you don't have this property, then I think it's usually you can very easily sort of construct situations in which sort of the behavior of your geometry is sort of different from the behavior of your gradient flow equation. Mm-hmm. So I think it's related. It's related to sort of having sort of uniform bounds on the convexity.
You also think it's tight, actually, that the uniform convexity bounds would actually be a tight criterion.
I'm not sure, but I would probably think so. Yeah.
Interesting. Thank you.
Okay, thanks. Is there any other question? Okay, so I think it's also time to end. Okay, this one word probability seminar. So first of all, I would ask everybody, I would invite everybody to unmute so that we can thank both the speakers again. So thanks a lot for these very nice talks.
Thank you.
Okay, so I thank everybody, and I hope to see you next week for the next one word probability seminar. Okay, thanks a lot. So
thank you.
Bye bye to everybody. So Jan, so can you create a PDF file with your slides?
Yes, yes. I will send it to you. Yes.
Okay, so we will upload on the website of the one word probability seminar. Also, Matthias, if you want to change something, otherwise, okay. You can, if you want to update your version, you can send us also tomorrow. It's not a problem. Okay.
Yeah, I'll do that. Sure.
Okay, so thanks a lot. It has been very inspiring, very interesting. Hot talks were extremely nice. I appreciate a lot.
Thank you very much from me as well.
And thanks for organizing. And it's nice that it works out so well. It's nice to see many people, many names in the list.
Yeah. Okay. So I greet everybody. I would close the room because we have now another meeting, always because of the one word probability seminar, but between organizers. So have a nice evening. And see you soon, I hope, so next week.
Okay, thank you. Bye-bye.
Bye, thank you.
Bye.
Bye-bye.
Bye-bye.